And in this lecture, we will talk about another type of gas power cycle, and which is the Brayton cycle, or which is used in your gas turbines. Okay, so what is the difference between the gas turbine? Before starting this lecture, we can just find out what is the difference between the gas turbine and your previous cycle, which we already discussed about in the previous lecture. Okay, so in the previous lecture, when we are talking about Otto cycle, diesel cycle, or wheel cycle, these all type of cycle convert your reciprocating motion into some sort of work. Okay, so that we use that reciprocating motion into and convert it into the work. But here in the gas turbine, what we have to do is we have to convert the rotary motion, okay, rather than the reciprocating motion. Okay, so this is the main difference between the gas turbine and the previous cycle, which we are already discussed. Okay, so now coming towards the production of the gas turbine. So here it is how it look like. Okay, so if you can just notice that the same thing you can see in your aeroplane engines, your jet engines, okay, which is also working on a gas turbine power plants. Okay, so gas turbine have been used for electricity generation, okay, in the period of peak electricity demand. So it has both of the uses in the automobile sector as well and in the electricity generation as well. And if you can just remember, I have already told you that whenever we have to produce some maximum efficiency for your power plant, we use your steam power plant and your gas turbines cumulatively so that we get the maximum efficiency out of those systems. Okay, so in this lecture, we only talk about the gas turbines. Okay, so gas turbine can be started and stopped quickly, enabling them to port into the service as required to meet the energy demand peak. So it has a small unit size, which is a very good thing, and their low thermal efficiency restricted the opportunity for their wider use for the electricity generation. That's why we use steam power plants and gas turbine cumulatively, because if we just use this system alone, it has a low thermal efficiency. Okay, so then the gas turbine, also called combustion turbines, a type of internal combustion engine in which burning of air fuel mixture produces hot gases that spin a turbine to produce power. Okay, so a similar thing we already discussed in the previous Otto cycle as well. That was also the internal combustion engines. Okay, so this is also the internal combustion engine. It is the production of the hot gases during the fuel combustion, not the fuel itself, that gives the gas turbine name. Okay, so we have to the production of hot gases. Basically, in the previous case, what we have to use is we just produce the combustion, and then due to the combustion in the Otto cycle and diesel cycle, there will be the conversion of your reciprocating motion into some sort of work. But here we get the rotating of the turbine, okay, or we get the rotation of some part by using the hot gases. Okay, we will see one video also, then you can better understand what's happening in the turbine as well. Combustion occurs continuously in the gas turbine. Okay, so this is another point. As comparison to internal combustion engine, in which there will be only two parts where the combustion takes place. Okay, so once we have to add energy and then we have to reject energy. Okay, so these are the two parts. If you can just notice over there, there will be two portions where we have to just add some amount of energy. Okay, so in this case, there will be continuously supply of your combustion process. Okay, so if you can just go towards the next slide. Okay, this is how your gas turbines look like. So in this gas turbine, there are some important components. So the main components are here. This part is your compressor. Okay, so where we have to compress the air so that we get the we have to increase the temperature of the air. Okay, so air is going inside. Okay, and then we can compress it, and then it will turn into the higher temperature. Okay, so after this part is your combustion chamber. Okay, so if you can just notice over there, there are small tubes that are fixed over there. Okay, so these small tubes are fuel injector basically. Okay, so where we have to inject the fuel. Okay, and then after combustion, there will be a turbine portion. Okay, and if you can also notice that these all components are connected with the one shaft. Okay, so it means that your turbine is producing work, okay, on the same shaft, and the compressor is also attached to the same shaft. Okay, so now we will see one video so that we will get the better understanding what's happening in the gas turbine. Okay, so basically this is your turbine. This is how it looks like. So these are the components. So compressor is there, combustor is there, and turbine section. Okay, so your air is going in from this part towards the compressor, and after it's sent to the compressor, there are several. So that is the air intake. Okay, now there is some turbine blades over there. Okay, so there are two set of turbine blades which we have to attach. One is the rotating one, and one part is the stationary. If you can just notice, this part is the stationary blades. This is the stationary, this is stationary, this is stationary, and these blades are rotating, and there will be an intake. Okay, similar to same happen over there also. Okay, so what is the purpose of these two set of blades? Okay, so these two set of blades, in order to we have to increase the pressure. Okay, so as the air passes through these blades, so the pressure will increase until it will reach towards this section. Okay, so that's why we have to use multiple set of blades for this one, and we call as the stages. Okay, so the air is passing through from all the blades. Okay, so here we called it as a low stage, and this is the high pressure stages. So now there is a combustion chamber. So air and fuel mixture will be sent together, and then there will be combustion. And if you can notice, this is your fuel injector. Okay, there are multiple fuel injector installed throughout your turbine section. Okay, and there will be ignition plug also, similar to your motorcycle, where there will be ignition process take place. So now here is the turbine section. Okay, so now there is the important part that in your turbine section, how we have to produce the work. Basically, all the combustion process will result in the exhaust gases. Okay, so we have to pass these exhaust gases through this blade section, which is also the stages, and then we convert this exhaust gases energy in order convert into the rotary form of energy. Okay, so will result in the rotation of the turbines. Okay, and as you can notice that because it is combined with the same shaft. Okay, your compressor is also on the same shaft, your combustion chamber is also on the same shaft, and turbine is also on the same shaft. So some part of the energy which is developed in your turbine section will be go back to your compressor section, and we have to use this work also in order to drive this compressor. So these are the some important components of the turbine, gas turbines. Okay, so I hope you will get some idea of it, and we will discuss more about it as well. Okay, so the thermal efficiency of the gas turbine is 20 to 30% compared with the modern steam power plant, which is 38 to 40%. Okay, so in future it is possible to construct efficiency in around 45%. So this is our main objective, that we have to develop such type of turbine so that we can achieve maximum efficiency for your gas turbine as well. So the following fields where we have to apply these gas turbines in practical. Okay, so there will be power generation industry, there will be oil and gas industry, aviation industry. We daily see that there will be jet engines, and then they use the gas turbines. Then marine propulsion also. And gas turbine is used in aviation and marine fuel because it is self-contained, lightweight, not requiring cooling water, and fit into the overall shape of the structure. Okay, so it is an important point that we don't require cooling water. As we see in the steam power plants, we need the cooling water in order to cool down the different energy, which is hot gases. Okay, so here the air which is going, which is intake from the compressor, is also doing some work in order to cool down the whole parts as well. Okay, so this is the main advantage of the gas turbine, and it is selected for the power generation because of its simplicity, lack of cooling water, quick installation, and quick starting. It is used in oil and gas industry because of cheap supply of fuel and low installation cost. So some limitation of the gas turbine, we can also see that they are not self-starting. So this is also one issue because in order to start the gas turbine, it is a main issue for the, because that's why it is not frequently used in your gas in the power generation process as well, because it is very difficult to start the gas turbine. Low efficiency at part load, non-reversibilities, higher rotor speed, and low overall plant efficiency. Okay, so what is the disadvantage of higher rotor speed? Because if there will be a high rotor speed, so it's mean that there will be more stresses on your rotor part. And when there will be more stresses, so it's mean we have to use some very hard alloys, okay, so that they will withstand for these high rotor speed. So that's mean we have to make our structure more rugged. Okay, so this we already seen in the video as well. So there are some basic components. So the turbine, the compressor, combustion chamber, and then there will be auxiliary devices like starting device, lubricating pump, fuel pump, oil system, and duct system. Okay, so same thing, the working fluid is compressed in a compressor, which is generally rotary and multi-stage type. Okay, so we already discussed that these are the different rotors blades, okay, which are installed. So as the rotor, as the air passes through these rotor blade, the pressure increases until it reaches towards the combustion chamber. Heat is added to the compressed fluid in the combustion chamber. Okay, this high energy fluid at high temperature and pressure then expand in the turbine and then generates the power. And part of the energy generated is consumed in driving the compressor. Okay, so which we already see in the picture in the video as well, because the turbine and your compressor is connected on the same shaft. So that's why some of the part of the energy which is developed in your turbine section in the form of rotary motion, it will be sent back to the compressor section as well. Okay, so here are the two different types. So we have to just classify the gas turbine into aeroderivative, which is used in your jet propulsion system and your jet crafts, and then there will be industrial type. So aeroderivative units are aircraft jet engine modified to drive electrical generator as a maximum output of 40 megawatt. These can produce full power within 3 minutes of the startup, and they are not suitable for the base load operation, okay, which is your daily life purpose. Then there will be industrial gas turbine, range in the size up to more than 260 megawatt, depending on the size. Startup can take from 10 to 40 minutes to produce the full output. Industrial gas turbines have the lower capital cost per kilowatt installed than aeroderivative unit because of their more robust construction and are suitable for the base load. So here, this is your industrial type. Okay, so if you can notice over there, it is a very big type of unit which is in order to produce the power, and this is your uh, aeroderivative type, which is used in your jet type jet units. Okay, so now looking towards the advantages of gas turbine power plant over diesel and steam power plant. Okay, so first advantage is that work well per kg of air is more than diesel plant, or also as comparison to the steam plants. Then there will be less vibrations due to the perfect balancing and no reciprocating parts. So I already told you that these are the rotary type of engines and there is no reciprocating motion involved in it. So that's why there will be less vibrations as well. Then less space requirement, capital cost is less, high mechanical efficiency. Okay, so that is the two different things, mechanical efficiency and thermal efficiency. Okay, so previously we talked about that it has the low thermal efficiency, okay, which is towards the complete cycle. The running speed of the turbine is large, low installation and maintenance cost. Torque characteristics of the turbine plants are better than the diesel plants. Ignition and lubrication system are simpler. Specific fuel consumption does not increase with time in gas turbine power plant as rapid in the diesel plant. Poor quality of the fuel can also be used and it is also lightweight and smokeless combustion is achieved in the gas power plant. So these are some basic advantages of the gas power plants as comparison to diesel and steam power plants. Now we will see some disadvantages as well. So disadvantages, poor part load efficiency. This I already told you that we need the special metals and alloy that are required for different components because there are high speeds are involved in it. Okay, so then special cooling method is required for cooling of the turbine blades. It has a very short life because there are many high thermal stresses involved in it. So that's why there will be a short life of all the components. Thermal efficiency is low, wide operating speed. The fuel control is difficult. Need to have speed reduction devices for higher operating speed of the turbine and then difficult to start the gas turbine compared to diesel engine. Manufacturing of the blades is difficult and costly and same output gas turbine produce 5 times the exhaust gases than internal combustion engine. So these are some disadvantages of the gas turbine power plants. So if you have any question you can ask me, then we'll move towards the next question. Okay, so working principle we already talked about. Air is compressed to high pressure, then fuel and compressed air are mixed in a combustion chamber. Hot gases, which are the exhaust gases, which spin the turbine wheel. Okay, so here we have to use hot gases or the exhaust gases to produce some work. Gas turbine burns fuels such as oil, natural gas, and powdered coal, and these are the components. Okay, so the detail of these components are mentioned over there. We already discussed in the previous section, so you have to go through it by your own. So there is a compressor, combustion chamber, and then there will be a turbine section. Okay, so the gas turbine power plant can be classified mainly into two categories as based on the cycles. Okay, so one is the open cycle gas turbine power plant, and second one is the closed cycle gas turbine power plant. So open cycle we mostly see in your jet propulsion type, where we have in this type of plant the atmospheric air discharged into the combustion through the compressor, and the exhaust of the turbine also discharged with the atmosphere. So as we see in the turbine as your jet propulsion engine video, where we have to intake air and then it will result in the combustion by using the air fuel mixture, and then the exhaust gases will be go towards the atmosphere. So this is the open cycle gas turbine. Then there will be a closed cycle gas turbine plants. In this type of power plant, the mass of air is constant or another suitable gas used as a working medium and circulate through the cycle over and over again. Okay, so we have to just make it a closed loop. Okay, so we will see that how your open cycles look like. Okay, so this is the open cycle schematic diagram. Okay, and most of your gas turbines, which is used on an open cycle. Okay, so here we are talking about that air is going towards the compressor. Okay, so after the compressor part, here we have to compress the air and it reaches the high temperature and pressure, and then it was sent to the combustion chamber. where there will be a fuel is added to air, okay, and then it will send to the turbine section, and once at the turbine section, the exhaust gases which are produced will result in the rotary motion of the turbine blades, okay, and then we will get some W net, which is the work, and then the exhaust gases are exit from the point number 4, and then it will be released towards the atmosphere. Okay, so this is the open cycle gas turbine engine. Okay, so the closed type gas turbine engine we usually call as a Brayton cycle. Okay. And in this cycle, we have to assume something. Okay, so as in the IC engines, auto cycle, dual combustion, and diesel engine, we already assume several things. For example, we have to replace your combustion chamber, which is where your combustion takes place, with the heat exchanger, and then we have to just add heat exchanger where we have to reject the heat, and then there will be a turbine as well, and then the compressor as well, and then all your working fluid will move towards the closed loop, okay, and it will circulate in the closed cycle. Okay, so this is the working principle of your gas turbine, which is the Brayton cycle. So in your Brayton cycle, we will see how your TS and TV diagrams look like. Okay, and most of the thermodynamic analysis we have to, because you already know that whenever we have to idealize something, we have to assume something that there will be a closed system, and then there will be the combustion process is changed to the heat rejection process, and your rejection process takes place from the heat rejection process, or your analysis of your thermodynamic cycle. So in this case, there will be 4 processes involved in the isentropic compression process, which takes place from 1 to 2, which is your compressor part. Then constant pressure heat reduction process, so which is from 2 to 3, and then 3 to 4, which is your isentropic expansion in the turbine. The similar isentropic expansion we already see in the Rankine cycle as well, because expansion takes place in the turbine, and then there will be a rejection of heat at your 4 to 1. Okay, so now we will draw the TS diagram first, okay, and then we will get the better understanding of it. Okay, so 1 to 2 is the isentropic process, so it means that your entropy is constant. Okay, so as you already know that we have to draw one straight line, which is from 1 to 2. So it represents your process 1 to 2, which takes place in the compressor. Okay, so now you already know that once, for example, at point number 1, your temperature is T1 and pressure is P1, and whatever the temperature at point number 2 is higher, and pressure is also increase, okay, because we have to compress the air, so that's mean the pressure will increase. Okay, so it's mean that the point number 3. Okay, so now at the point number 3, which is at the end of your combustion process. So at the end of the combustion process, the temperature will increase. So it's mean that this point number 3 will be somewhere there. Okay, because it will be result in the increase in. Okay, and then from 2 to 3 it is a constant pressure heat radiation. Okay, and then 3 to 4 again it is the isentropic process, which is the expansion process. So in the expansion process, your temperature decreases. Okay, this is point number 4, and then as it will be a 4 to 1, there will be a rejection of heat. So it's mean that whatever the temperature at point number 4, the point number 1 temperature will be lower than the 4. Okay, these are little bit curves. Okay, so you have to draw it. I will show you in the next slide. Okay, so this is the Q in, which is at constant pressure, and this is your Q out, which is also at constant pressure, and then 3 to 4 is your expansion process, and 1 to 2 is your compression process. Okay, so this is the TS diagram for your Brayton cycle. So if you have any question, you can ask me. Then we will draw the PV diagram as well.
सर ये 2 से 3 और 4 से 1 स्ट्रेट लाइन होगी कर्व?
2 से 3 आपके पास होगी कर्व लाइन होगी, क्योंकि ये है कांस्टेंट प्रेशर हीट एडिशन प्रोसेस है और 3 to 4 आइसेंट्रोपिक प्रोसेस है, तो सिंपल स्ट्रेट लाइन होगी, एंट्रोपी कांस्टेंट।
Okay.
So now looking towards the PV diagram, so we will draw the PV diagram as well. Okay, so 1 to 2 is your compression process. So you already know that whenever there will be compression, so it's mean that your volume will decrease. Okay, so it's mean that if your point number 1 is there, okay, so it will turns into point number 2 will be somewhere there. Okay, so this is your point number 2. Okay, so now 2 to 3 is the constant pressure heat addition process. So it's mean that your pressure is constant until point number 3. 3 to 4 is the expansion process. So it's mean whatever your volume is at point number 3, after expansion, which is at point number 4, your volume will increase. Okay, so it's mean that your point number 4 will be somewhere. Okay, then 4 to 1 is your again constant pressure heat rejection process. So it's mean that this point and 4 is on the same. So this is your 2 to 3 is Q in and 4 to 1 is Q out. 1 to 2 is your compression process and also entropy is constant over there. And this is your expansion process. Also S is equal to constant. So this is the PV diagram for your Brayton cycle. So if you have any question, you can ask. Then we will move towards the some derivation, which is related to the efficiency, because our end product is to find the efficiency of the cycle. Okay, so we will derive one relation for the efficiency of the Brayton cycle. Okay, so these are the Brayton cycle PV and DS diagrams, so that you can clearly correlate with it. Okay, so this you can go through by yourself. Okay, this is the efficiency equation. Okay, so we will try to derive this equation, how this equation comes from, and then there will be another term which is used for the Brayton cycle is the pressure ratio, which is the ratio for your maximum pressure, which is at point number 2, and your minimum pressure, which is at point number 1. Okay, so this is also called P3 over P4 as well, because your pressure at point number 3 is equal to P2 and pressure at point number 4 is equal to P1. Okay, so in the theory, as the pressure ratio goes up, the efficiency rises. The limiting factor is frequently the turbine inlet temperature, and the turbine inlet temperature is restricted about 1700 Kelvin to 2600 Fahrenheit. Okay, so these are some things which you have to. Okay. Now we will see that how to develop the efficiency equation. Okay, so I will just quickly draw the PV diagram so that you can easily. Okay, so as you already know that whenever we have to develop the equation, we have to start from the energy balance equation. Okay, so in this case, we already know that Q in is at the constant pressure. Okay, so we can say it will be equal to Cp T3 minus T2. So we already know that this is for the constant pressure process. Okay, and then whenever there will be Cp values involved, so we can also say that it will be equal to H3 minus H2. Okay, so we already know from the previous knowledge as well. Okay, then Q out. So Q out is also on the constant pressure. Okay, so we can say Cp T4 minus T1, and then we can also write H4 minus H1. Okay, for the efficiency, you already know that W net over flowing. So from here 1 minus Q out over Q in, which is equal to 1 minus Cp T4 minus T1 over Cp T3 minus T2. Okay, Cp will eliminate from there. Okay, so now we are left with 1 minus T4 minus T1 or T3 minus T2. Okay, so for the process 1 to 2, we know that this is the isentropic process. Okay, and for the isentropic process, we already know that we can write the relation that T2 over T1 for the isentropic relation is equal to P2 over P1 K minus 1 over K. Okay, so this we already know from the start of your gas power cycle lecture that these are the relations which are valid for your isentropic processes. Okay, so similar thing, because in this case we already know that your P2 is equal to P3 and P1 is equal to P2. Okay, and then we can say that for the process 3 to 4, T3 over T4 is equal to P3 over P4 and K minus 1 over K, which is a specific heat ratio. Okay, so from here we can say that this P2 over P1 and P3 over P4 is equal to pressure ratio, which is RP. Okay, we already discussed that this is the ratio for the maximum pressure over minimum pressure, which is P2 and P1. Okay, and from here we can also write that T2 is equal to T1 RP is the pressure ratio K minus 1 over K, and we can also say that T3 is equal to T4 RP is the pressure ratio K minus 1 over K. Okay, so you have to note it down, then we'll move towards the next part. If you have any question, you can also ask. So as the efficiency equation is, we already know that it is equal to T4 minus T1 over T3 minus T2. Okay, so now we have to plug all the values of T3 and T2. Okay, in the equation which we already drawn in the previous slide. Okay, and then we will see that what turns out to be T1 and T3 is T4 pressure ratio, which is RP K minus 1 over K, and minus T2 is T1 RP K minus 1 over K. Okay, so if we can just take RP from the denominator common, okay, so and then the T4 minus T1 can be eliminated. Okay. turns out to be RP K minus 1 over K. Okay, so this is the efficiency for your Brayton cycle. Okay, so if we have the value of pressure ratio with us and we need to know the specific heat ratio for your working fluid, we can easily find the efficiency of your Brayton cycle for the, and this is valid for your cold standard air assumption, okay, only, okay, and the air standard assumption. And for the variable specific heat values, we have to use the enthalpy values, which is enthalpy value at point number 2 and 3, and enthalpy value at 4 and 1, in order to find the efficiency of your Brayton cycle. So you have to note it down, then we move towards the next. If you have any question, you can also ask.
Sir, is this pressure ratio is same as we already studied about the ratio between high pressure and low pressure?
Yeah, it is the meaning is same. Where we have to discuss about the beta, I think you have to denote it with the beta, the pressure ratio in your dual cycle.
Yes, sir.
Yeah, and it is the same thing. Okay, only we have to present with the RP. So it is also the pressure ratio, which is the same for the dual cycle, but definitely the working principle of the dual cycle is different, and the Brayton cycle is different.
Okay.
Okay, so another thing which I have left over there, okay, there is another term which is the work ratio, okay, and which is called the back work ratio. Okay, so what is the back work ratio in the Brayton cycle? So as I already told you that because your turbine and your compressor is connected on the same shaft, okay, so here we have to define back work ratio based on this, that the fraction of the turbine work used to derive the compressor is called the back work ratio. Okay, and the back work ratio we have to say that BWR, which is equal to W compressor, which is the work done for your compressor, and then your turbine work, W turbine. Okay, this is the ratio of these two terms. Okay, so if you have mentioned in your problem statement that you have to find back work ratio, okay, so then you have to just divide these two terms, which is your compressor work and your turbine. Okay, and this we have to just say that this is the fraction of turbine work which is used to derive the compressor, and that we have to represent with the back. Okay, so I think we will take 10 minutes break, and then we will again join after 10 minutes, and then we will start one example related to the written cycle. 10 minutes break. starting from the example related to the Brayton cycle. Okay, so which is the gas turbine based on gas power plants. Okay, so this is your example 9-5 from your book. So gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. So RP is given in your question. The gas temperature is 300 Kelvin, okay, at the compressor inlet. Okay, so you have to know that the compressor inlet is at point number 1. Okay, you can correlate with the TS term. And 1300 Kelvin at the exit of the at the turbine inlet. Okay, so turbine inlet or that is at point number 3. Okay, if you can just correlate with the TS term. Utilizing the air standard assumption and variable specific heat, determine the gas temperature at the exit of the compressor or in the turbine, the back work ratio, and the thermal efficiency. Okay, so basically in your 9-6, we have to use 9-5. Variable specific heat, okay, in order to find these part number A, B, and C, and then we will compare the efficiency by using the air standard assumption. Okay, and you have to calculate all these three parameters by using the air standard assumption as well. Okay, but we have to use variable specific heat because we need for the back work ratio we need the value of enthalpies. Okay, in order to find these part number B. Okay, the thermal efficiency we can easily find from both of the air standard assumption as well. We just need the value of RP, and RP value is given in your question. Okay, so we just plug the value in the equation of the efficiency for the air standard assumption normal, and we can find out the efficiency. And for the variable specific heat, we need the enthalpy value. Okay, so we have to note down the data, then we will start the problem. So quickly draw the TS diagram first. Okay, so in your question, it's mentioned that T1 is given in your question and T3 is also given in your question. Okay, so starting from the T1, okay, so T1 is mentioned that it is equal to 300 Kelvin. Okay, so you just have to go to table A17 and you just have to find the value of enthalpies at all the points. Okay, so that you can easily find the values of your part number A also, which is we have to find the temperature at point number 4. This is part number A, and part number B is the back rotation. Okay, so you just have to go to table A17 and find out the value of enthalpy H1 against this temperature, which is the same procedure which we already discussed in the previous lecture as well. So 300.19 kilojoule per kg is the value of H1. Okay, and then we have to find the enthalpy value at point number 2 as well. Okay, so we need another parameter. So you have to just note down the value of relative pressure for point number 1. Okay, by using the same T1, which is 300 Kelvin, by using the table A70, 1.386, the value of relative pressure. Okay, so we already know that 1 to 2 is isentropic process, and for isentropic process, we can write PR2 or PR1 is equal to P2 over P1. Okay, and in your question it is mentioned P2 over P1, which is the value of RP, is the pressure ratio, maximum pressure P2, and P1, which is equal to 8. Okay, and PR1 we have find in the previous step. So from here we can easily find the value of PR. 1.386 and RP value is 8. PR2 value turns out to be 11.09. Okay, so now we have our parameters, so we can easily go to table A17 again and we can apply interpolation by using this reference value, and you have to apply first interpolation to find the value of T2, which is 540 Kelvin, and then we can apply the next interpolation in order to find the enthalpy value at point number 2, which is 544.35 kilojoule per kilo. The interpolation procedure is the same, which we already discussed in previous lecture. Okay, so coming towards the process 3 to 4, okay, so we have already know the value of T3, which is mentioned in your question. The T3 value is 1300 Kelvin. Okay, so from here we can directly find the value of H3 by using the thermodynamic table, and it will be equal to 1395.97 kilojoule per kg. And similar thing, we also have to find another parameter, which is the relative pressure at point number 3, which is equal to 330.9. And from here we can say that for your isentropic process, which is between 4 to 3, it will be PR4 over PR3 is equal to T4 over T3, because we have to find the value of T4. Okay, so that's why we need the value of another parameter at point number 4. And you already know that Rp is equal to P3 or P4. Okay, and if you can just say that you have to find that P4 or P3, so it is equal to 1 over Rp, so 1 over 8. So PR4 value turns out to be 330.9, is the PR3 value, and 1 over 8, which is the inverse of your pressure ratio. Okay, and if we can just find the value of PR4, it will be 41.36. And by using this value, PR4, we can easily go through again thermodynamic table A17 and apply the interpolation by using this reference value. And we will find the value of T4 for the first interpolation equal to 770 Kelvin. And then we have to also apply for second interpolation because we need the value of enthalpy. So it turns out to be H4. So H4 is equal to 789.37 kilojoule per kg. Okay, this is the part number A. So our main target is to find the T4, which is the part A, and we have to find the exit of the temperature at the exit of the compressor and the turbine. So you have to note it down, then we move towards the next step. So for part number B, So in the part number B, we have to find the back work ratio. Okay, so we already discussed that the back work ratio is the ratio for your compressor work. Okay, so which is the compressor in, okay, because we have to supply the work towards the compressor and then turbine out. Okay, so first part we have to find the compressor work. Okay, so the compressor work, if we can just correlate with the TS diagram, we can find that the compressor is installed between 2 and 1. Okay, so H2 minus H1, and we already find the value of enthalpy at point number 2, and also we have already find the value of enthalpy at point number 2 in the previous part number A. And H1 value is 300.1. From here we can easily find the value of. Similar thing for turbine out. So H is installed between 3 to 4 your turbine, and we need the value of enthalpy at point number 3, which we already find in the previous part number 8, which is 1395.97 and 789.37, and it turns out to be 606.6 kilojoule per kilo. Okay, now we have both of these two things. Okay, so we can just divide the value of compressor work, which is 4.16 to 606.6, and we will get the back work ratio, which is 0.403. Okay, so that is this means that 40.3% of the turbine work output is used to drive the compressor. Okay, so this is the meaning of your back work ratio. This is part number B, so you have to note it down, then we move towards the part number C. So in the part number C, we have to find the thermal efficiency. Okay, so for thermal efficiency, we need the value of W net and Qing. Okay, so Qing, you already know that your heat is supplied between point number 3 to 2, okay, so which is H3 minus H2. So H3 is known to us from the previous part number 8, 1395.97. H2 is also known to us from the previous case, 35, and Qin is equal to 851.62 kilojoules per kg. So for W net, okay, so W net you already know that it is equal to W out minus W in. Okay, so W out is we already find in the back work ratio, which is part number B, which is equal to turbine out. Okay, so turbine out work is 606.6, and W in is in the compressor part, which we have to supply to the compressor, which is 244.16, which we already find in the previous part number B. So from here we can easily find W net, which is 362 point. 4 kilojoule per kg. So from here we can easily find the efficiency, which is 362.4 divided by 851.62, and that turns out to be 42.6% of your thermal efficiency for your Britten cycle. Okay, so this is the part number C. Okay, so similar thing, we also apply the cold standard assumption to find the thermal efficiency, and for this we can just need, if we can compare with the old standard assumptions, so it will be 1 minus Rp, which is the pressure ratio, K minus 1 over K. Okay, so if we can just put the value, because Rp is known to us, so value is 8, and then it will be 1.4 specific heat ratio of the air divided by 1.4. It turns out to be 44.8%. Okay, so this, if we can just compare these two values by using two assumptions, we can easily compare that there will be significant difference in the efficiency. And which value is more closer? This value is more closer towards your actual, which is calculated based on variable specific heat assumption. Okay, and this whole layer standard assumption, basically we have to solve by using many assumptions in order to derive this relation. That's why this value is not closer to the actual value. Okay, so you have to note it down. If you have any question, you can ask me, and then move towards the next question. Okay, so this is another question which is from your book. Okay, so there is 9-77 from your book. Okay, so stationary gas turbine power plant operate on a simple ideal Brayton cycle with air as a working fluid. The air enters the compressor at 95 kilopascal. So T1 is known to us, and T1 is also known to us, which is 290 Kelvin, and the turbine at 760 kilopascal and 1100 Kelvin. Okay, so main point number three values are also known. Heat is transferred to air at a rate of 3500 kilojoule per second. So its mean Qin is given to us. Determine the power delivered by this plant, and assuming the constant specific heat at room temperature, we have to find this power delivered by using both of the assumption, which is first is constant specific heat and then variation of specific heat. Okay, so you have to note on the problem data, then we will move towards the solution. So for the part in A, which is assuming the constant specific heat, okay, so first we will draw the TS diagram so that we can coordinate with it. So 1 to 2 is your compression process, then there will be a heat radiation process 2 to 3, then there will be expansion process, and then there will be a heat rejection process. So T1, which is 290, is given in your question, and T3 is also given in your question, which is 1100 Kelvin. Okay, so for first part, we have to use the equations. Okay, so we have to apply one equation, which is between point number 2 to 1, okay, which is the isentropic process. So for isentropic process, we already know that T2 over T1 is equal to P2 over P1, K minus 1 over K specific heat ratio. Value. Okay, so now we have to know the value of, okay, so we have the value of P2 over P1 with us, which is the pressure ratio, which is the value of 8, and T1 value is also known to us from the question. So we can easily find the value of T2. So it will be 290, 8. Okay, so pressure ratio, I think it will be not given directly. So you have the pressure value in your problem. So you have to just divide the values and you will get the pressure ratio. So it will be 1.4 minus 1 over 1.4. And from here we get the value of T, which is 525.3 Kelvin. Then also we need the value of temperature at point number 4 because T3 is known to us, so we have to find the value of T4 as well. So T4 over T3 is equal to P4 over P3 K minus 1 over K. And from here we can easily find the value of 1100 Kelvin, and P4 over P3 is equal to inverse of over pressure ratio RP, which is equal to 0.4 1.4. Okay, and from here we get the value of T4, which is equal to 607.2 Kelvin. Okay, so now both of these temperatures are known to us, so we can easily find the thermal efficiency. So for thermal efficiency, we already know that 1 minus T4 minus T1 divided by T3 minus T2. Okay, so this equation we already see in the previous lecture as well. So we can simply put the values 1 minus 607.2 minus 290, 1100, 525.3, which is value of T2, and it turns out to be 44.8%, which is the thermal efficiency. Another important point is that we also use the relation, which is the efficiency is equal to 1 minus 1 over Rp, K minus 1 over K. Okay, and simply we put the value of Rp, we can easily find the thermal efficiency. But important point is that what procedure you have to adopt, it is on you. So you have to use any procedure. If you can simply use this one, you can also get answers. Because this is for the old standard diffusion. So for part number B, we need the values of enthalpies. Okay, so you have to note down, then we can move towards the next part. Okay, so coming towards the part number B, which we have to find the. Okay, so in the part number A, we have to find W net. Okay, so in the W net, we have to multiply efficiency with the queuing. So this is similar for the part number A. Okay, because our main thing is to find W net. Okay, so efficiency we already find, which is 0.448 to 44.8%, and Q in value is known to us from your question, which is 35,000 kilowatt. Okay, and if we can just multiply, it turns out to be 15680 kilowatt for your W. Okay, so this is the part number A by using the 4-layer standard convention. Now part number B, we have to find similar thing with the W net by using the variable specific heat. Okay, so in order to find the variable specific heat problem, so we need the value of enthalpy. Okay, so temperature 1 is known to us in your question, which is 290 Kelvin. Okay, so we can just go to table A17 first, and we can easily find the value of H1. This H1 is 290.16 kilojoule per kg. And also we need another parameter, so we can find the relative pressure at point number 1, and we can just go down against this 90 Kelvin, 1.2311, and from here we can easily find the value at point number 2, okay, the enthalpy value. So first we need the relative pressure at point number 2. Okay, it's a similar procedure we already talked in the previous example as well. Okay, and from here we can easily say that PR2 is equal to 8, which is the pressure ratio, and then 1.23 double, and that turns out to be 9.8488. Okay, and from this value we can easily go to table A17, and again you have to apply the interpolation, and you can find the value of H2, which is equal to 526.12 kilojoule per kg. Okay, so now we have the value of H1, we have the value of H2, so we have to find the value of H3 also and H4 also. So H3 value we can easily find because T3 is mentioned in your question, which is 1100 Kelvin. So simply you can go to table A17 and find the value of H3, 1161.07 kilojoule per kg. And you also have to note another parameter, which is relative pressure, which is equal to 167.1. So now we have the value of H3 with us, and now we have to find the value of H4 also. Okay, so in order to find the H4, we can simply apply the relation for the isotropic process, which is 3 to 4. Okay, and we can say PR4 is equal to P4 over P3 into PR3. Okay, and P4 over P3 is equal to burst of your pressure ratio, so 1 over 8, and PR3 value is 167.1, and we can find out the value of PR4 as 20.89. So we can use this value 20.89 by using the interpolation. We can easily find the value of H4. So you have to apply the interpolation by yourself. It's the same procedure which we already discussed in the previous lecture. So 651.37 kilojoule per kg is the value of H4. Okay, now we have the value of H4, H3, H2 with us, so we can easily find the efficiency. So you have to note it down, then we move towards the next. If you have any question, you can also ask me. So for efficiency, we already know that it is minus Q out over Q in, and your Q out is between 4 to 1. So we can say that due to H4 minus H1 and Q in, which is H3 minus H2. Because we are using the variable specific heat. Okay, so we have all the values with us. H4 is 651.37, H1 value is 290.16, H3 value is 1161.07, and H2 value is 526.00. Okay, and from here we can easily find the efficiency value, which is 0.431 and is equal to 43.1%. So from here we can also find W net, because our main objective is to find the power delivered by this plant, and W net is equal to efficiency into Q in. So efficiency is 0.431 and Q in is mentioned in your question, which is 35,000 kilowatt, and from here we can easily find the power delivered, which is 15085 kilowatt of your equipment. Okay, so this is the solution for your part number B. So you have to note it down, then we will go to the next one. Which you have to solve. So this is a simple one that I already solved in the previous problem, which is 9-77. So only the temperature values, which is this one, is different, and then this value is also different from the previous one, and you have to determine the power delivered by this plant by using the constant specific heat at room temperature assumption and by using the variation of specific heat with temperature. Okay, on all